Ladies and gentlemen, my name's Joe Engelberger. I have been the founder and chairman of Unimation, and Unimation eventually was the company that promoted and sold to General Motors and others the Puma robot. I want to, first of all, abdicate the role of being an inventor. I wasn't. The inventor is sitting next to me, and he has with him today some co-inventors who also contributed, and I'm sure we'll hear from them as we go along. Let me start with prehistory. Unimation was already a company building hydraulically powered robots of various sizes that worked largely in the automotive industry. And it came to pass that a young guy came to a show, I think it was Robots 3 in Chicago, and we had a big booth there. Unimation had its robots on display, AMF, a number of other companies were there. Happy to say that Unimation was the dominant booth. And outside in front of the building, there was a guy sitting there, a long-haired fellow with something under his arm. And these days, the police would have arrested him. But there, people stood around and watched. He had a little robot under his arm, just a little rascal. And people gathered around. I looked there at passion, and I invited him to come in and have a table about so big in our booth, right at the corner of the next company's booth. And again, he gathered a crowd around him with this little robot. And the people in the next booth got very upset because the little old machine, which I believe at the time had the name of the MIT robot, worked quite fine, and their big monster robot was having all kinds of trouble. It was a harbinger because that particular competitor is no longer in the business. Anyway, even stepping back further, you have to realize that Vic was a maverick. He started building a robot at Stanford, and it became known as the Stanford Robot, and it used the geometry of the helpmate kind of a thing, a coordinates arm that rotated and went in and out. And then he moved his thoughts to MIT, and he built this little one that had the same kind of articulations as the Puma, but just a little rascal. And I thought a lot of that. I thought it was good. And then I can't even remember, maybe Vic will, why we were walking around a lake in Poland. But anyway, the two of us were walking around a lake in Poland, and I said to him that, you know, you should join Unimation, and we should really try to do something with the electric robot. And one way or the other, we did it. So we merged, and out of that was born Unimation West. And now it's time, I think, for Vic to explain just what Stanford Arm, MIT Arm, and all the things that happened from them on to make it eventually, technically now, the Puma Arm. Vic, please.
Okay. Okay. Well, I can look at the photos. My name is Victor Scheinman, and I consider myself a roboticist, slightly retired right now, but you want some biographical information. Let's see, as a young kid, I was always intrigued with mechanical devices and electrical devices, electronic devices. My high school subject was a voice recognition system, which is well documented, as it seems, through some television appearances back in the 50s. I went off at a young age to MIT and wanted to become an aeronautical and astronautical engineer. In fact, that was my bachelor's degree area. We did some projects such as I was president of the Model Airplane Club. I was, for those who went to MIT, I was a master craftsman in the hobby shop, and the typical things that sort of a nerdy, gadget-minded guy likes to do. I graduated from MIT and went off to work for Boeing for a while. And I ended up at Boeing I only wanted to work for 6 months or so there. I worked for the fellow who, my boss essentially became the next president of Boeing. So when I got to Boeing, I was put on the little company chart, and it went the president, my boss, and me. I had sort of there of just doing some independent research. A year later, I went to Stanford as a aeronautical and astronautical major. Immediately switched into mechanical engineering when I realized that I sort of enjoyed that field better and had more freedom to think and design and develop things on my own. I got my master's there, and then the next year I continued on and got a research assistantship working for the computer science department, artificial intelligence lab, doing some robot design. The first year I worked on developing a device we called the ARM, which was a digital robot, a snake-like device. The concept was digital computer, robot. It had a load capacity of one little mini light bulb, let's put it that way, and it could flex about 100 degrees or so in any direction. After that, I worked on developing a hydraulic, a 6 degree of freedom hydraulic manipulator, with the concept that computers are fast, robots could be fast. To build a fast robot to work with a fast computer. We found out that that really wasn't the case in those days. The computer was slow relative to the robot, in the sense that the computing systems we were using at the time were time-sharing mainframe computers, PDP-6 computer, and just to run the robot required essentially continuous full-time processing from the robot. After that, I developed an electric robot, which was much more compatible with the university environment, the computer room environment. No hydraulic fluid on the floor. When the hydraulic robot ran, it was on an elevated floor. The whole building would shake because of the forces that were put into the floor. The electric arm was then developed. This was called we had learned about designing a robot to simplify the kinematics, simplify the arm solution, so that we could do real-time control with less computation. For instance, the concepts of intersecting axes, orthogonal axes, things of that sort. This arm starred in quite a few of the early projects of the Artificial Intelligence Lab at Stanford.
Can you hold up the picture for the camera so we can...
Hard to see it.
Describe what it is.
This is the Stanford Arm here. And it's actually assembling a water pump in this application with visual guidance. Here, there's a camera system here, an old Vidicon camera system. And in fact, I developed some features to the camera which allowed it to be panned and tilted. And in fact, we could even get some color information with color wheels. It was a black and white camera system. And some of the features of this arm were that since the computer was required full time to control the arm, and it was a time-sharing system, we had to hold the arm in positions while the computer went away and did other jobs. And so the arm would move through a control path for a few seconds, and then it would stop, and the computer would go off and service all the other users, or else do some other computation, then it would start on again. And it is a 6 degree of freedom arm, and was the prototype of several built. The other universities and other organizations were interested in the ARM. This was in 1968 and 69. In 1971, Professor Marvin Minsky at MIT had an idea that it would be good if universities around the country and around the world could have a lower cost way of doing, well, call it hand-eye research work, in other words, robotics work. And he wrote a proposal to ARPA, the Advanced Research Projects Agency, a mini robot project in which he proposed to have a smaller robot, might be a desktop system, a lower cost camera system, and of course somewhat lower cost computers. And in fact, it anticipated the fact that the cost of computing would come down. And the concept was to have a sort of little mini competition to have people design a robot for this application. And he invited me to MIT. I guess it was 1972, to be one to design a robot for him and for this project. And his assignment to me was build the smallest robot you think you can build that's practical and might be reasonable cost. And that was pretty much it as far as the specification goes. He talked a bit about the fact that it should be probably electric and should have, it was going to be computer controlled, 6 degrees of freedom, issues of that sort. I spent several months at MIT, mostly in the design phase, and I did bring I found one of my notebooks where I did a lot of my sort of thinking.
Do you have it here?
Yes, I do.
Can you just hold it to describe what
Well,
you're doing, or
it's
too
hard
to see?
it's hard to see. I mean, it's, you know, like 100, 200 pages long. Unfortunately, I don't have. I might have a few of the early drawings, but I don't have the full set. I think they were
Might
left.
show the-
What?
the
Yeah,
picture.
right. Anyhow, I designed the ARM, and the process I used essentially was I did all the calculations, all the drawings were all done by hand, but not sketched. I mean, I used drafting techniques. And in fact, as I typically did it, I would essentially design the whole thing, all the joints, all the motors, all the specification, everything ahead of time. And when I left MIT in several months, I essentially had a cost breakdown of what it would cost to make all these parts. I went back to Stanford, and MIT at that time said, Vic, well, we want you to build us a few of these robots. Right, okay, so I'll show you this. So anyhow, and we'll jump ahead a little bit. GM will explain what they wanted, and this is what we ended up delivering. And I might say delivery was a little bit of like really giving birth. It occurred, for us, it occurred at 2 in the morning. And when I drove it in my back of my pickup truck to the airport, because that was going to get it on the last plane. We promised them the next day, and I knew that there was a flight at 4 in the morning, a freighter flight to Detroit, which would get in the next day. And typical of me, we ran out of gas on the way to the airport, and I had to run down the street and find a gas station that was open and get there, but we made it. This is the robot mechanism itself. It's in this case, it's only a 5 degree of freedom robot. Later, we did add 6 degrees of, an extra degree of freedom. But it's a 5 degree of freedom robot, and it has a gripper on the end. The gripper is a later device. It's not one that we actually delivered. The one we delivered had a parallel, which was done according to a GM design time. And then later, we started making our own grippers. It's all electrically powered. You can see one of the motors in here. This is one of the motors that powers the 1st degree of freedom. There's another motor system. There's more motors in this body here, and there's some more motors inside here. It has a 2 degree of freedom gear, so it can move up and down. I can't really rotate it because the brakes are on. In other words, it has electromechanical brakes that sort of lock it in position. So if everything sort of fails, it doesn't collapse. Again, it has the monocoque construction, the shell type construction. This case here is a 1/16 of an inch thick, a thin shell, and the components are essentially to that shell. It produces a stiff, strong, lightweight construction. Later versions, production versions of it, had more castings on it. This didn't have aluminum castings or almag castings. This is all made out of machined aluminum. Some of the other components that we delivered with it were the controller. This is the controller for the Puma robot, the microprocessor, which was a 16-bit single-board computer, essentially, designed and built by Digital Equipment Corporation, called the LSI-11. And it was compatible with the other PDP-11 series computers from a software standpoint. So it enabled us to port a lot of the early software which we had developed for computers like the 1145 into this computer here. And in fact, that was one of the keys. Early on, people were enamored with the 8-bit microprocessors, the 8080, the Z80, the Intel and Zilog processors, or the MOS technology, 6502s like in the Apple computers. But we realized at the time that they just were powerful enough. They just did not have the capability to do what we wanted to do in the software and the control. In addition, inside here are the power amplifiers, the computer interface to the power amplifiers, and the power supplies for the robot itself. A cable ran from this box to the computer. The user interface to the system was through 2 components. This is the original terminal that I guess we delivered with it. It's a 80 character, 24 lines, or whatever it is, 40-line text display monitor. And it allowed you to essentially write programs, read programs, look at the status of the computer on a black and white screen. In addition, there was what we called, I guess, we called what, the ICM, was it? The Interactive Control Model
We
Module?
call it a teach pendant.
Or the teach pendant, right. Or the teach pendant, which was supplied for the robot. And it allowed you to do some manual control of the robot. And the interesting thing about this device is that it had various modes. Not only could you, for instance, push a button that said free robot such that it was totally limp and you could move it around manually. It had joint mode, which allowed you to run individual joints at a time, which is essentially pretty much how everybody else used to move their robots in those days. And then it had a world and a tool mode. In world mode, and that was a strong feature of the VAL system, which Bruce had developed. The computer controlled the robot in real time and was able to do coordinate transformation, ARM solutions in real time. So that if you push this button and then you move the knob, you could actually move in Cartesian space. Even though the robot is an all-revolute joint arm, it could actually move in Cartesian space. You could move in Z or X or Y, and you could do rotations about those axes. And it would all be done in real time. The other mode was what's called tool mode. You're flying an airplane and you're sort of sitting in the cockpit is the end of the gripper here, in which you, if you wanted to go forward, that would be sort of like in the Z direction, fly ahead. If you wanted to fly in X and Y, that would be sort of yaw or flying off to the side or up and down. So we could actually put a tool coordinate frame in the coordinate frame in the tooltip and run the arm as if you were doing that. And the nice thing is that you could teach the robot to sort of move into a hole very easily. And of course, the major component that's not seen here is the software that was associated with this robot. The valve software, which of course was inside here, and stored in that case on a floppy disk drive, and also internally. And that allowed the robot to do these sophisticated motions, to move in real time with these sophisticated motions, the valve software. I think that sort of is a brief survey of it. I might say that the box itself is roughly shaped this size because the robot itself, as delivered originally, sat on top of the box in a case which would bolt it right to the side of the assembly of the conveyor belt, the special assembly line. So imagine this robot sitting on top of a box which is right around this thing. The whole unit could be just essentially lifted up and carried away completely as a single unit, except for, of course, this terminal. In operation, the terminal wasn't necessary. It's just used for programming and instructing the robot with writing the programs.
You might want to just mention also about the microprocessor servo control.
Right, right. It had a multi-mode microprocessor servo control. In fact, besides the LSI-11 inside, it had a microprocessor, an 8-bit microprocessor for each of the joints of the robot arm. The microprocessor was a 6503. Actually, it's exactly like the 6502, which eventually the computer that was in the Apple computers of those days, a 8-bit microprocessor. So we said this was the equivalent of having 6 Apple computers inside, as well as this LSI-11. So it had this microprocessor on a microprocessor per joint control. It also allowed us to control it in some different, potentially in some different forms, current position servos, velocity servos, things like that. But essentially, the servo loops were closed in the microprocessor, which was running full-time on the joint, whereas traditionally people had sort of closed the servo loops in hardware. And it did give us some more flexibility in adjusting things like gains and the performance. We were able to greatly reduce the number of manual adjustments that you needed to make. I think that sort of covers a brief introduction to the robot. I might say that one of the other interesting things about it was that originally the robot had this big square box here. And the idea was, my dream was to eventually take all the electronics and all the software, all the computers, and put them right in here and have the brains in the head. And that's what this space was in large part reserved for.